All right, we'll start off with some review. We're in Lewis structures for covalent compounds. That's molecular compounds, things where we've got nonmetals bonded to other nonmetals. This is sort of kind of more the bread and butter of Lewis structures and where we're going to be spending most of our time. So as a reminder, our first step, we want to come up with a skeletal structure. We want the bare bones of what we think our molecule is going to look like. For this class, we don't really have a good selection tool for figuring out what's a good structure or a bad structure. So the idea is we want symmetry. If you take 1A, you'll learn some of those tools, formal charges, to be able to come up with, quote unquote, good Lewis structures based on some other rules. But for now, symmetry is our goal, and usually it's going to be stuff that's a little bit more obvious than this H2CO. So we came up with this basic skeletal structure before we put any bonds in. Then we added up all of our valence electrons. We learned about valence electrons somewhat recently. We can either do an electron configuration, count up all the electrons in the highest n number. So like for carbon, it would be 2s and 2p2. And we get 4 electrons. Or we can go based off of the column, the group number. So looking at the farthest number on the right, so 1, 2, in 13, that would be 3a, so 3 valence electrons, 14, 4 valence electrons, 15, 5 valence electrons, etc. And so we add up all of the valence electrons that we have, and we're going to figure out how we put those on the board. The first way that we put those on is as bonds, because everything needs to be connected. So we'll just put in the minimum number of bonds that we need to connect everything. And I use the nomenclature BE for that, just bonding electrons. And then what we have left, what we had left was 6 remaining electrons. And we placed those starting from the outside, working our way in. Oxygen, since it only had 1 bond, was able to hold those 6 remaining electrons. And so all of our electrons were placed. And then we went through and checked, do our hydrogens have duets? 1 bond, so they have their duets. Perfect. Does our oxygen have its full octet, 8 electrons on it? It did, with 3 lone pairs, 2 electrons each, so 6 electrons from lone pairs. And then 2 electrons also from that bond. So oxygen was happy with its full octet, but carbon was short too. And so we moved in one of these lone pairs off of oxygen to bond with carbon, and we ended up with this Lewis structure in the bottom left-hand corner. For our final Lewis structure, all of our octets filled, or duets in the case of hydrogen. So we're going to be drawing some more of these. If we're doing Lewis structures for polyatomic ions, a couple of these show up on the Lewis structure worksheet. We do need to pay attention to the charge of the ion when we calculate the number of electrons for the Lewis structure. So like if we're doing a Lewis structure for sulfate, SO4 2-, this 2- means add 2 electrons. So we'll have the 6 that we have from sulfur, we'll have the 24, 6 times 4 from oxygen, and then we add 2 on top of that. If we had something like NH4+, this 1+ means subtract 1 electron. So we would add our 5 from nitrogen, our 4 from each of our total hydrogens. That would be 9. We subtract 1, so we end up with 8 valence electrons that we would place for those. And then when we end up making these Lewis structures, let's pretend like I drew the Lewis structure in there. We also have to do brackets and charge. So we have to show our charge and our brackets. That's because this whole thing together, the brackets, this entire structure, whatever we would get for SO4, has a negative charge. It's not that the 2 negative charges on the sulfur or on the oxygen, just overall we've got 2 extra electrons. And so we indicate that with the brackets and the charge in that upper right-hand corner. let's do an easier polyatomic ion. We want to write a Lewis structure for the cyanide Cn- ion. So our first step, we want a skeletal structure. So our skeletal structure comes first. We do a decent amount of 2 or 3 things, just 2 or 3 atoms, and they're very easy. You can almost not get it wrong. You could get it wrong, though, if you're thinking in 3D space and you put them on top of each other, because that's just confusing. So don't do that. Just put them anywhere you want, as long as they're not on top of each other. So our skeletal structure, C, N, might as well put it in the order that they show up. So that's our skeletal structure. You could have also put it NC, maybe. Doesn't really matter. So we've got our skeletal structure, piece of cake. And then we want to count up our valence electrons. Carbon on our periodic table, we can find it in group 14. It's all the way at the top, number 6. It has 4 valence electrons. We've got 1 carbon, 4 valence electrons total. We also have 1 nitrogen. And our nitrogen is in group 15, so it has 5 valence electrons. And then we also have 1 extra electron because of the charge. Oop. That 1 extra negative. So that's 1 more valence electron. If you forget that valence electron, you're going to have the darndest time figuring out a Lewis structure for Cn-. Okay, so our total number of valence electrons is 10. 10 valence electrons. Now we need to get everything connected, place some of our electrons. We need 1 bond to get 2 atoms connected. So 2Be. We have 8 remaining electrons, Re. Since we have just 2 atoms, we can place those 8 electrons evenly across the carbon and the nitrogen. How many electrons do each of those get? Correct, it's 4. I think somebody said it. If you didn't say it, I heard it anyway. So we placed 8 electrons. Okay, no electrons left. Now we need to go through and check our octets. They're going to be the same. We've got 1 bond, that's 2 electrons. And we've got 2 lone pairs, so that's a total of 4 electrons. Nitrogen has 6 electrons. That'd be a hextet, which is not what nitrogen wants. Nitrogen wants an octet. So we need to bump up the number of electrons that nitrogen has access to. How can we increase the number of electrons nitrogen gets? Yeah, carbon can share, right? So nitrogen needs a little extra. Carbon is happy to share. Carbon says, okay, I'll share a pair of my electrons with you. So this would turn into this. Trying to maintain all my colors. And I shifted over the double bond for the carbon. Now if we look at nitrogen, we've got 2 lone pairs and 2 bonds. 4 plus 4, that's 8. Okay, so nitrogen is good. How many electrons does carbon have access to? It has 2 bonds, a double bond. So that's 4 electrons, and 2 electrons in lone pairs. So carbon only has 6 electrons, and so we have to do the same thing. Nitrogen is then going to share one of its pairs in. And we would end up with carbon triple bonded to nitrogen. So they each have 8 electrons. Okay, so they both got their octets. Anything else we need to do or check? Yes is the answer. We have not put in our brackets. So since we have an ion, we need our brackets and our one negative charge, and now this is a complete Lewis structure. You don't necessarily have to add in each of these lone pairs one at a time. You can do them at the same time if you see that that's what we need to do. You don't need to show me every single step. So this would be our complete Lewis structure for the cyanide ion. Questions? Great. One for you to try. Write the Lewis structure for the ClO- ion. ClO- is hypochlorite. I'll give you a couple minutes to work on that, and I'll play my memory game. All right, coming back after our short pause. We want the Lewis structure for the ClO- hypochlorite ion. So first up, we want our skeletal structure, chlorine and oxygen. Nice and easy. Then we want to count up our electrons. Chlorine is going to have 7 valence electrons. Oxygen has 6 valence electrons, and we also need one more from our negative charge. So that's going to be 1 extra electron. So 7 plus 6 plus 1, we get 14 valence electrons that we get to place. And we're going to start off placing those with 1 set in between our chlorine and our oxygen, just to get everything connected. So that's our 2 minimum bonding electrons. Then we've got 12 remaining electrons. We can split up 12 electrons between 2 targets by putting 6 on each. So we've used up all of our electrons. All the electrons are on the board, and we can check our octets. Oxygen has 2 electrons from its bond, and it's got 2, 4, 6 electrons from lone pairs, so oxygen has an octet. Oxygen's happy. Chlorine, having the same number of electrons, same exact setup, also happy. So that is a complete Lewis structure for ClO-. Almost. We need our brackets, and we need our 1 negative charge outside of those brackets. If you forget to add in that 1 negative electron, or that 1 electron from the negative charge, what you would end up getting if you forget the 1 extra electron, you get bamboozled. You would end up with chlorine bonded to oxygen. One of them is going to have 6 electrons, the other one will have 5, and you are never going to get those to both have full octets, because chlorine has 8. So chlorine, in this case, the way that I've drawn it up, would be happy. Oxygen has 7 electrons. If we share in some electrons from our chlorine, share a pair to make this a double bond, then oxygen would have 9 electrons. That's also not a full octet. So you'll end up getting into a sticky situation like this. So usually if you end up with an odd number of electrons, that's not a good sign. Questions about that Lewis structure? Great. We also have exceptions to the octet rule, so sometimes we will only be able to end up with some odd electron species. That's typically not going to be the case, so we're mentioning it here just so that you know it can happen. It shouldn't happen for anything that you have to do for the class, though, just because it's confusing. So for example, if we did NO, nitrogen has 5 electrons, oxygen has 6 electrons, we would end up with 11 total electrons. Right, 11 valence electrons. We would end up with a double bond. That's 4, so we'd have 7 of our 11 left. We'd place 4 on oxygen, 3 on nitrogen. That does actually exist in nature. It's stable. It's confusing because nitrogen doesn't have a full octet. But that happens sometimes. Won't happen for you in the class, I think, maybe on the homework, but it's not going to happen on a test or on the Lewis structure worksheet. Another important exception to the octet rule is boron. Aluminum will also do this, or can do this, where it only has 6. Only 6 electrons instead of a full octet. Boron, a bit of an oddball because of that. I'm pretty sure boron doesn't show up on the Lewis structure worksheet either or on the exams. It's just something to know for the future. So if you're going to take 1A or 1B, this is good to know. There are also some atoms, some elements that can have more than 8 electrons. And we call these expanded octets. So expanded octets occur only on, I think it's row 3, period 3. And lower, 4, 5, etc. elements. So things like phosphorus and sulfur on our periodic table, you'll find those over in our P block. Right, they're in period 3, and those can have expanded octets. If you're curious about why those can have expanded octets, you don't need to know this for the class, but some people are probably interested. So the way that the expanded octets work is they put the extra electrons in the empty 3d orbitals. So that's why they're able to hold more electrons. That's also why it won't happen with anything that's in period 2, because they don't have access to the 3d orbitals, so they don't have those like kind of extra secret pockets all over the place like some jackets have to hide those electrons in. On the Lewis structure worksheet, there's an explicit like section of expanded octet things. So that's how you know to do an expanded octet. Otherwise, we're going normal octet rule. We also have a thing called resonance. So when we write Lewis structures, good Lewis structures for some things like SO2, we can write more than one good Lewis structure. So we would lay out our skeletal structure. Looks kind of like a bear. Also, right? Anyway, sulfur in the middle so that we've got that left-right symmetry. Oxygen, 2 of them. So we've got a total of 12 electrons. We've got 1 sulfur, that's going to be another 6 electrons. So we've got 18 electrons to place. We can connect the sulfur with its neighboring oxygens with 2 bonds. So using 4 electrons just to get everything connected together, we've got 14 remaining electrons. Why did I write it that way? 14 Re. And then we need to place those electrons. We're starting from the outside and working our way in, so each of these oxygens can take on 6 electrons. So 6 electrons to each of our oxygens. That leaves us with 2 left. And so those 2 electrons then go on the sulfur. If we look at our octets, oxygens have full octets. Sulfur has 6 electrons. Do some rearranging here. So sulfur needs a double bond. We've got 2 oxygens that can share to form those double bonds. So are we going to take from the left or the right? And the answer, some of you might have been thinking it, yes. We're going to do both of those actually. And so this is going to, after I copy paste, we've got our red arrow option and our purple arrow option. Let's clean some of this up. So if we pull in this lone pair from the left oxygen, then we've got sulfur with a double bond, a single bond, total of 6 electrons, plus the 2 in the lone pair. So sulfur now has its full octet. The left oxygen didn't lose access to any of those electrons. It still has its octet. The right one still has its octet. If we pulled it in from the other side, it looks like the mirror image. So we've got the double bond on the right side instead, and everything has full octets. So in cases like this, we draw both structures, and then we would do a big double-headed arrow to say that it's actually switching between these two, the way that we can draw our Lewis structures at least. In reality, it's probably not one of these or the other. It's a hybrid of the two. So in reality, the bond strength is more like 1.5 between the sulfur and each of the oxygens rather than 2 on one side and 1 on the other side. We don't have the tools to draw that, at least for this class, so that's what we get, is resonance structures. And for full points, to be completely correct, you do have to draw both for resonance structures and include the little arrow. Questions about Lewis structure stuff so far? All right, so again, either one of those 2 Lewis structures predicts that SO2 contains 2 different kind of bonds. When we examine it in nature, we find that both of the bonds are equivalent and something in between. So we might draw it with 1 full line and dashed lines, and I'm not going to draw in the rest of the electrons. So it might be something like that. Just like if you breed 2 different, varieties isn't the right word. 2 different breeds of cats together, right? You'll get out something that's kind of in between. It's got some of the properties of one, some of the properties of the other. So that's what it would look like. and we need both structures and the arrow. Otherwise, it's not correct. A word of warning. Danger. A word of warning about the Lewis structure worksheet. When you're doing the Lewis structure worksheet, make sure that you use the information that we've learned in class. We've learned an incomplete picture of how to put together Lewis structures. If you are familiar with the words formal charges, if that rings any bells in your mind, forget about it. Don't use formal charges. If you end up using formal charges on the Lewis structure worksheet, make sure that you show that you know how to use the formal charges. If you have no clue what formal charges is, great, that's awesome. You don't have to worry about it. But if you look things up for the Lewis structure worksheet, occasionally you'll come across a correct answer, and I don't expect you to get the correct answer. So that tells me that you looked it up, and you probably also didn't do it correctly, even though you looked it up. And so then I get to nuke your grade, drop the hammer on your Lewis structure worksheet grade. So don't do that. Instead, just use what we learned in class so that you get as many points as possible. All right, would you like to watch me do another resonance structure example, or would you like to try it yourself? A or B? Lots of B's? All right, then get busy, B's. All right, it looks like people are sort of wrapping up their structures, or they've given up. So, starting with our skeletal structure, I already drew it up here. Our skeletal structure is oh no. And then we're going to count up our valence electrons. And this is a place where if you screw up counting up your valence electrons, you will be saying oh no, because you'll end up with an odd electron count. So we've got 2 oxygens. Each of those oxygens has 6 electrons, so we've got a total of 12 electrons. We also have 1 nitrogen. The nitrogen has 5 valence electrons, and it's an ion. So we have a 1 negative charge. That means 1 extra electron. So our total count is the same as we saw with SO2. 18 valence electrons that we get to place. So we're going to start off by connecting everything. So connect our nitrogen to its neighboring oxygens. So that's a total of 4 minimum bonding electrons just to get everything connected. We've got 14 remaining electrons. You might be feeling a little bit of deja vu. We can place those electrons, 6 on each of the oxygens, and then the last 2 on our nitrogen. So 12 electrons to oxygen, make that a big O, and 2 to our nitrogen. That's all of our electrons up and on the board. And if we do our counts, we will find out oxygen is good to go. Nitrogen is short. It needs 2 more electrons, and so we're left with a decision to make. Pull in from the left for those electrons or from the right. And of course we say yes, we will do that. And we do both. So we'll end up with 2 structures. My brain is telling me that there's a Shakespeare reference that I could make there, but it's not telling me what exactly it is. So, apologies, you don't get to enjoy that. Okay, so after we draw in our resonance structures, it should look something like that. Double bond on the left, double bond on the right. All of our octets are fulfilled and satisfied. What are we missing? Yeah, we're missing brackets. We're also missing our arrow. So we need that double-headed arrow, and since these are ions, we get to put brackets on them with the one negative charge outside the brackets in the upper right-hand corner. Questions? So part of the fun of Lewis structures is that we can use Lewis structures to do more stuff. So if you thought, wow, Lewis structures is a lot, don't worry, there's more. So we're going to add on to our Lewis structures. We'll get a Lewis structure, and then we can use what some people incorrectly, in my opinion, call VSEPR theory. That's valence shell electron pair repulsion theory. VSEPR theory or VSEPR theory, not VSEPR, because that's the wrong order. So valence shell, electron pair repulsion. Valence shell, outside, right, our outside electrons. Electron pairs, bonds, and lone pairs. And last but not least, repulsion. They repel or push away. So the whole idea behind valence shell electron pair repulsion theory, VSEPR or VSEPR theory, is that our electron groups are negatively charged. And just like magnets, if you get the negative parts together, right, those will push each other away. The electron groups do the same thing. So the bonds, those are electrons. Our lone pairs, those are also electrons, and so they're going to spread out as much as possible. That's the entire idea behind VSEPR theory or VSEPR theory. So we've got four groups that show up in this class. We've got lone pairs, just two electrons. We've got single bond, one line, double bond, two lines, triple bond, three lines. Those are all made up of electrons. Electrons repel each other. And they spread out. We can use that idea to figure out what our molecules look like how they're arranged in space, where the bonds are, where the different atoms are. So we can predict shapes of molecules. If we have something like CO2 carbon dioxide has this structure. This is what you should come up with if you were having to draw it by yourself. Our CO2 has two electron groups, the two double bonds on the central carbon atom. The furthest that two things can get away from each other if they're connected in the center is opposite sides. So we get 180 degrees of separation between our double bonds. So it's like if my body is the carbon and my hands are each oxygen atoms, just putting my hands out. Right. Showing my dominance, T-posing on the class. So that's the furthest that they can get away from each other, and that looks like a line. So we call that linear geometry. Also, if we only have two groups, 2 points defines the line, so those are also going to be linear. It's like the CLO that we saw earlier. CLO minus, also linear. In my book, at least. In my mind. So anytime we've just got two things, that's also linear. Although I think our book might call it something else. I disagree. So that's one of our shapes, one of our geometries. We have other shapes. So for example, this H2CO that we drew up kind of early in our Lewis structures adventure. We reviewed that at the start of the lecture. We've got 3 groups on our central atom. So our 3 groups on carbon spread out. And the most that they can get spread out is about 120 degrees from each other. And we call this trigonal planar. The tri of trigonal, like 3, and the gonal part, I believe, means points, or 3 parts. And planar, just meaning that it's flat. So like on the projector or on your screen or whatever, right, this is in the plane of whatever it is you're looking at. So it's sort of like the Y shape that you do in the YMCA song, kind of like that. It's upside down here. I'm not going to do a handstand like that. I definitely could, but I'm not going to. So that's one of our other shapes. Questions about our 2 shapes so far? Our 3rd shape, we'll use methane as our example, so CH4. We have 4 groups on our central atom. And you might be thinking to yourself, well, 4 groups will just spread out in the plane, but these exist in 3 dimensions. And so while you might think that it's making an X with your body, we can actually spread out our groups a little bit more. So my feet are each a group and my hands are each a group. If we twist, then they can actually spread out a little bit further because the distance between my hands and feet is slightly further apart. So it's not 90 degrees, it's 109.5 degrees, which is a number that you just get to memorize because that's fun, isn't it? So it's not square planar, although that is a shape, not a shape that we use in this class. It's tetrahedral. So that tetra meaning 4 and hedral meaning sides. If you were to imagine a plane forming between each of these 3 hydrogens, every group of hydrogens, this is what a 4-sided die looks like. It's a D4, the carbon hiding in the middle. So tetrahedral, 4 sides, it's a D4. Questions about any of our shapes so far? We also have things that have lone pairs in them. So this brings us to the idea of electron geometry. What do our electron groups look like? And molecular geometry, what does it actually look like? Because electrons kind of don't exist. They're real, but like they don't take up space. So that's why we have a different arrangement. Our molecular geometry, because our atoms definitely take up space and they're kind of sort of locked into a spot, and our electrons are just kind of wherever they want to be. So for NH3, we would come up with a Lewis structure like we see here on the right. We've got 3 bonds, 1 lone pair. So we still have 4 electron groups. And that's going to be the tetrahedral shape. That's our shape that our electron groups have. So doing our X and then twisting 90 degrees to the left or to the right. All right, so that's our electron geometry, but one of those groups is lone pairs, and so we just kind of get rid of it. And you'll notice now I've got 3 points, but they're not in a plane. Right? I'm on the ground, not 10,000 feet in the air. One of them is deflected out of because of this electron group. It's forcing that other group kind of out of the way. And so it's still trigonal because 3 groups, but it's more of a pyramid shape, which you would see if I put one of my hands down on the ground, but I just don't feel like doing that today. So the lone pair forces the bonds away from it. And one of the reasons that I stand up here and do the posing out the shapes, partly it's fun, it's silly, it's goofy. Also, you can do this. This is something that you can do to practice your shapes. I have yet to have anyone take me up on doing that during an exam, but hey, it might happen someday. So in the safety of your own home, in the comfort, the quiet, the not having other people looking at you, feel free to practice these, or like imagine what it would look like, because they can help. We also have one more shape that we'll talk about. So H2O, we've also seen this Lewis structure before. We still have 4 electron groups. So we've got a tetrahedral electron geometry. So do our X, twist to the left. But 2 of those groups are electron pairs. And if those disappear, now it's just me with my feet spread wide apart. So that's like a bent shape. Or if you imagine my feet disappearing and my hands just being up in the air, that would also work, but I'm not good at levitating yet, so also not going to do that for you today. So we get this bent molecular geometry. We can get that with 2 lone pairs and 2 bonds. There's another way that we can get bent geometry. It can be with 1 lone pair and 2 bonds. All right, so if we hit the YMCA pose with our feet together, or the praise the sun, right? If we imagine that my feet don't exist, then the hands up in the air, that's also bent geometry. Or if I get rid of one of my hands, that's dangerous. That would also be a bent geometry, right? That bent shape. So those are the 5 shapes for the class. There's also, if you have a hard time visualizing spatial arrangements in your head, you don't feel like posing things out, there's a table that you can use to get the same answers. So this is the one from the book. I think I give this to you even on exam 3. I don't remember for sure though. So check the information sheet. It might be on there, it might not be. But if you practice posing through them, or if you're good at visualizing things in your head, it's not necessarily that difficult. All right, so predicting our geometries using valence shell electron pair repulsion theory. We need to first draw a correct Lewis structure. So that's got several steps built into it. Once we've got our correct Lewis structure, assuming it's a correct Lewis structure, then we determine the total number of electron groups around the central atom. That's lone pairs and bonds. It's a number from 1 to 4. We'll also determine the number of bonding groups and the number of lone pairs. And then based on those, you can either refer to table 7.7.1 from the book to figure out the electron geometry and the molecular geometry, or you can imagine me standing up here doing the poses and then like getting rid of a hand, or you can pose through it yourself and try to get those things spaced out as much as possible to come up with your electron geometry, what the electron group's shape is, and the molecular geometry, what the molecule actually looks like. So we're going to come up with some geometries, some shapes using our VSEPR, valence shell electron pair repulsion theory. What is the approximate shape of each of these molecules? We've got PCl3 and NOF. So for PCl3, we're going to have phosphorus in the middle. We can put chlorines around it. Phosphorus is in group 15, so it has 5 valence electrons. And we've got 3 chlorines. Chlorines each have 7 electrons, so we've got 21 electrons from those. Total of 26 valence electrons. Just to get everything connected, we need 3 bonds. So our minimum bonding electrons is 6. That gives us 20 remaining electrons. Each of our chlorines can hold 6 more electrons. So we can place 18 of our electrons on the chlorines. And we've got 2 left. Those 2 can go on the phosphorus. Then we would check our octets. Do we have full octets on our chlorines and our phosphorus? Yes, we do. We sure do. So our chlorines each have 3 lone pairs and 1 bond. Total of 4 groups, 2 electrons each. Total of 8. Our phosphorus has 1 lone pair and 3 bonds, so it also has 8 electrons. So we've got full octets. Perfect. So that's step 1 of our VSEPR theory geometry thing. Right, come up with a good Lewis structure. Then we want to figure out what's our central atom. Phosphorus is the central atom. So phosphorus, being the central atom, has how many electron groups on it? We have 4 electron groups. That's our combination of bonds and lone pairs. And that's made up of 3 bonds and 1 lone pair. So our electron geometry is just based on the number of electron groups we have. We've got 4 electron groups. That means that we've got tetrahedral electron geometry. That's the X-twist. That's our tetrahedral shape. That's what our electron groups look like. If we get rid of one of those groups, because one of them is a lone pair, we've now got 3 groups left. That means it's going to be trigonal something. Is it in the plane or is it off plane? It's off plane because of that lone pair forcing that 3rd group away. So it's trigonal pyramidal. So trigonal pyramidal molecular geometry. Wow, just getting right into that corner. Questions about that shape? All right, and then we have NOF. And we are helpfully told that nitrogen is the central atom. So we're going to have nitrogen in the middle, oxygen on one side, fluorine on the other side. It's really fun how a lot of these read out as things. Okay, so we've got fluorine, nitrogen, oxygen. We can do our little count of electrons. Fluorine's got 7, nitrogen's got 5, oxygen has 6. So we've got 18 electrons. Connect them with one bond between everything. We've got 14 remaining electrons. We'll place those so 12 electrons to our outside groups, fluorine and oxygen, and then 2 electrons to nitrogen to use up all of our electrons. And you might recognize that fluorine's got a full octet, oxygen has a full octet, and nitrogen only has 6 electrons, so this would probably lead us into a resonance structure sort of thing. Fortunately for us, we're just asked about the approximate shape of the molecule, so we don't have to draw out the Lewis structures necessarily. We just need, like the resonance structures, I mean, we just need to figure out what's the shape going to be like. So let's just draw it in with the double bond just from the right side and leave the other resonance structure out of it. So showing only one resonance structure. How many groups do we have on our central atom of nitrogen?
4.
It's not 4.
3.
It's 3. We have 3 electron groups. So double bonds and triple bonds only count as one group. So 3 electron groups. That means that our electron geometry is trigonal, planar. So it's flat and it's got 3 things sticking off of it. Our distribution is that we have 2 bonding groups and 1 lone pair. And so our molecular geometry is what? We've got 3 groups, or 3 groups. Get rid of one of them, it's bent. So our answers for these would be trigonal, pyramidal, and bent. Questions about getting either of those? Another thing that we'll be doing with the Lewis structure worksheet is there's a page where we'll be going over making them with molecular modeling kits, and that can be a helpful way of visualizing what these different shapes look like, since it gives you something physical to touch. You can also do it with like marshmallows and toothpicks. It's another way of doing it. If we did marshmallows and toothpicks in the lab, though, you wouldn't get to eat them, so molecular modeling kits. Feel free to eat your marshmallows at home. All right, one for you to try. Predict the molecular geometry of the SO3 2- ion. All right, our molecular geometry for our SO3 2- ion, we need to first come up with a good Lewis structure. I'm going to run through the Lewis structure just in case that was holding people up from doing the geometry stuff. We're going to have our sulfur in the middle, oxygens on the sides. We've got a total of 26 valence electrons. We'll get everything connected with 3 bonds. That's 6 bonding electrons. So we've got 20 remaining electrons. We can place 6 on each of our oxygens and 2 on our sulfur. That's all of our electrons gone. Put brackets around it, give it a 2- charge, and we've got our Lewis structure. I don't expect you to be able to do it that fast, but just to speed run you through it, and then I'll give you a little bit more time in case you're working on the geometry stuff. All right, so that was a tiny little bit more time to think about geometry. I think we probably have all identified that sulfur is the central atom. So we're looking at what things are connected to sulfur. On sulfur, the way that we've drawn it up, the way that we know how to draw it up for this class, we have 4 electron groups. And within those 4 electron groups, 3 of those are bonds. We've got 3 bonds and 1 lone pair. So if we imagine that X and twist shape, that's our tetrahedral, that's our electron geometry, get rid of one of those groups, and then we're left with trigonal pyramidal geometry. Or if you just refer to the table, 3 bonds and 1 lone pair, that's trigonal pyramidal. Questions about that one? There's also, for drawing things on paper, a special way of how chemists draw things. So chemists will typically use these notations for bonds to indicate 3-dimensional structures on 2-dimensional paper. If you happen to have 3-dimensional paper, congratulations. I don't know what that looks like, but you don't need to use this nomenclature. So our straight lines, just regular normal line, that's in the plane of the board. / on the paper. That's along the face of the paper. We also have hashed lines. Hashed lines go away from us. Or into the paper, or the board, or the screen, or what have you. And we have wedged lines, and the wedged lines are coming toward us, or out of the paper, or the board, or the screen, or what have you. You'll also occasionally see empty wedged lines, partly because I feel like getting the hashed lines right to make it look really good is difficult, and just doing an empty wedged line is kind of the same idea. So that's another way you can represent it. And the way that I remember, or the way that I like to talk about remembering these two, is wedged lines. There's a food that comes in wedge shapes. What is that? Cheese comes in wedge shapes, and cheese is good. I'm thinking of potatoes. Potato wedges, right? Potato wedges, I want to eat potato wedges. Wedge lines coming towards me. Potato wedges also better be coming towards me. So I'm eating those potato wedges. That's the wedge lines coming out of the plane of the board. The hashed lines, there's a reference there as well. Keep that stuff away from me, whatever you want to think of it. And you can draw out. These are just some representations of the molecular geometries. So in our linear, it's flat. In our trigonal planar, you can draw it 3-dimensionally with one coming out and one going back. Or you can also draw it like this bent shape, but instead of E here, it would be an X. The E just stands for electron group or electron pair, and X is just something else. So there's a bunch of different shapes and ways that you can draw stuff out. You won't, I think, really have to do this for the class, but it's a good idea to know that it's out there and to be able to draw like this. Questions? Okay, so we will be picking up here next week and adding to this. So my recommendation, review over the weekend.